Moment. Okay. Now, Professor Jacques Ferland. He is the Université de Montréal, Canada. The title is okay. Thank you very much, Professor Jacques. Come in this the new edition of ISORA. Okay. Okay.
Sorry for the delay in installing the machine. I usually take my machine with me to be sure that I won't get stuck with another machine. First of all, well, good morning to all of you, and let me mention that I'm very happy to be here for a meeting in honor of my very good friend Jacques A. And today I will talk about a more applied research on which we are developing some kind of a decision support system. But I will tell you part of the story. And in this part, the interesting idea is to merge together an exact procedure. Dinkelbach procedure is an exact procedure. You get optimal solution with this technique. And we introduce and we combine this exact procedure within what we call meta-heuristic. This technique that are not guaranteeing to get an optimal solution, but usually we can get very good solution. And in practice, we often use this kind of technique. So this is an example where we can merge exact procedure with meta-heuristic to improve the solution we can get with the meta-heuristic using an exact procedure. So first of all, let me tell you how I came to this problem. A student in computer science in trying to develop integrated system came to me to see if operations research can help him to develop technique, optimization technique to improve the system that they can develop. And that's how I came to this area. And we developed a okay, let's see. I hope my email will appear. So he came to me and we tried to develop some kind of a system to help a designer to develop the chips. So in this problem we have two sets: a set of processor and a set of data unit. The processor calls data unit to get the data and to improve the result. So using these two sets, the first thing was to see how we can group data units and processor that are very active or interacting very much, and to put them together in the subsystem in such a way that the processor might call on other data unit, but mostly it will call the data from the data unit within the subsystem. So this was the first step. The second step was to find a way to assign these groups of processor and family of data units to the node of the architecture. And the third step was to see how we can select the link with the proper capacity, allowing the interaction to go through the nodes. Okay? So these are the three steps that we identified. The first one is related to what we call the self-formation problem, and that's the one that I will discuss today. The second one is referred to the quadratic assignment problem. And for this problem, very good meta-heuristic procedure exists to solve it. And the third one is, well, we call it the bus selection problem. In fact, it is related very much to the problem of identifying the link in an electric distribution system. So there's for each problem, there is a link with a known problem. But for the self-formation problem, we first start to look at the literature, and we developed what we think very good meta-heuristic to get very, very good solution. And we developed this for the self-formation problem. But then the idea was to see, well, how close are we to the optimal solution? Are we far from the optimal solution or not? So the next step was to try to solve this problem with an exact procedure. And that's where we use the Dinkelbach procedure. Okay? And as we will see, with our meta-heuristic, which are much more faster to solve the problem, we can get optimal solution obtained with the Dinkelbach procedure. So that, in fact, we try to solve the problem exactly after we develop meta-heuristic to see how close we are to the optimal. Okay, so my presentation will go as follows. I will start to review briefly the Dinkelbach procedure, which is very straightforward technique. Okay? And I won't go into the detail. I will only specify the procedure as it is. Then I will use it to solve the self-formation. But we were able to solve only very small problem. Okay? For larger problem, we were not able to get optimal solution. Because this, as you will see, the problem are quite difficult to solve. And in fact, the problem is NPR. And the third part would be to see how we can integrate this exact procedure, Dinkelbach, within meta-heuristic method to solve the problem. Okay? How much time do I have? Overall. So from now I have 45 minutes? Okay, good. So the Dinkelbach procedure, well, it's a technique to solve programming problem where the objective function is a ratio of two functions. So this is a technique to solve fractional programming problem. Okay, so roughly speaking, you have two functions, f of x and g of x, and you try to minimize the ratio over the set of points belonging to some feasible set. Okay. Now you have this idea, and the feasible set is a subset of Rn. The functions are both continuous on an open set containing the closure of x, and finally, g of x, the function and the denominator must be positive. Okay? So, associated with this problem, we have the following parametric problem, obtained as follows. You specify different value of lambda, and you take the difference between the numerator and this scalar times the value of the function at the denominator. So it's nicer problem because you don't have a ratio function. Okay? So the problem is easier to solve. And the idea is to find a way to specify different value of lambda in order to get a solution, which is the solution for the original problem. This is the trick of the procedure. Okay, so we have these two problems, and then we can show quite easily that the function, well, of course, f of lambda is concave, right? Because the function here is defined in lambda. Secondly, we can show that the function is non-increasing. Okay? So it appears like that. Third, we can show that if the problem here has an optimal solution, then the value of f of lambda star, the value of the associated problem specified with lambda star, is equal to 0. Also, whenever f of lambda is negative, lambda is larger than or equal to lambda star. It goes both ways. And finally, which is the most important property, if f of lambda star is equal to 0, then both problems have the same set of optimal solutions. So, in other words, finding the root of f of lambda is equivalent to solve the problem, the original problem. Okay? So, let's take a lambda, scalar lambda k. Assume that xk is an optimal solution for the associated problem. Okay? Then it is easy to see that if we evaluate the function g at xk, we get a subgradient of the function minus f, evaluated at lambda k. So, based on this observation, we can use the idea behind the Newton procedure to find the 0 of the function f of lambda. So the idea is to identify the root of f of lambda, we can use the procedure behind the Newton method. So the next value of lambda you can get is equal to the value of lambda minus the value of the function at lambda k divided by the derivative or the subgradient of the function at lambda k. And making substitution, the lambda k simplify, and then we get finally easily the value of lambda k plus 1. So you see the procedure is quite simple to implement. And at each iteration, you have to solve this the associated problem, okay, which does not include the ratio of the two functions. Okay? So the Dinkelbach procedure goes as I described before. So you start with a certain x0 in the set x. Then you specify lambda 0 as the ratio of f and g over at x0. Then you solve the associated problem for, in general step, okay, you have a certain lambda k available and you want to get the next lambda k plus 1, okay? So, at the general iteration, you solve the associated problem at lambda k, you get a solution, call it xk. Then the stopping rule is the following. You try to find the zero of f of lambda. So if f of lambda k is close enough to zero, according to the constraint specified by the user, then we stop. And lambda k is close to optimal value, and xk is close to an optimal solution. Okay? Otherwise, we use the idea of the Newton procedure, and we get the value of lambda k plus 1, and then you repeat the process. So this is very easy to implement procedure. Okay. If we look at how the procedure is going, you see that since the lambda k are the ratio of f over xk, and lambda star is the minimum when you take over x over this ratio, then you see that the lambda k that you get are on the right-hand side of lambda star. It can be shown that the sequence is monotone decreasing, and furthermore we can show that the convergence is superlinear. This is quite an interesting procedure to solve fractional problems. We will see that solving the problem we want to solve, the objective function include a ratio of two functions. Okay, so that's why we turn to Dinkelbach procedure to deal with it. So let's move to see how we were able to solve self-formation problem with small size. Exactly with the Dinkelbach algorithm. Okay, so the self-formation problem is usually introduced in the context of cellular manufacturing, where you have a set of machines providing service to parts. And the idea of the self-formation problem is to subdivide the system into subsystems in order to maximize the interaction between the machine and the part that are in the same subset. This is the idea of the problem. So let's take an example. Here you have 7 machines and you have 11 parts. And there's a 1 in the matrix whenever, for instance, the element ij is equal to 1 if machine I providing service to part j. This is the definition. So the idea is to make subset of machine and parts that are interacting very much. They are, in a sense, you want to partition the area where you work in such a way that the machine are grouped to provide service to a set of parts. Of course, you have some part that have to be serviced by some machines that are not in the subset. But the idea is to reduce the number of one that are not in the block. This is the main idea. So this is formulated as a self-formation problem. Okay, this problem is shown to be an NP-R optimization problem. So in general, you should not try to solve these problems with exact procedure whenever they get large. That's why most people use heuristic procedure, meta-heuristic procedure to get good solution, or solution satisfying the users. Here we have to put ourselves as a person who want to provide service or to suggest solution to the user. So the idea is to get good solution, most of the time in a very short solution time, in order to satisfy the user. Okay, good. So let me formulate the problem so that we can see how we can use the Dinkelbach procedure. So we assume that we have a set of machine and a set of parts. And you have a matrix, an incidence matrix, indicating the interaction between machine and part. That is to say, Aij is 1 whenever machine I process part J. So the idea is to specify what we call cell. So we fix the number of cells, because in our context, we want to find subset to be assigned to a set of nodes in a given architecture. So we know the number of cells to produce. In general, the cell formation problem, you don't fix necessarily the number of cells. But in our case, we fix the number of cells. Okay, so each cell includes a subset of machine and a subset of parts. Okay? And the idea is to get a very good solution. Okay? And the objective to specify what is a good solution is provided by an objective function that we refer to as the autonomy of the system. There are several autonomy measures that are used in the literature. But most of the time, people designing procedure to solve this problem like to use what we call the grouping efficacy to compare different procedures. So we use this measure to develop our meta-heuristic. And the idea is very simple. You try to maximize the number of 1 within the block. And you divide by the total number of 1 in the matrix. And to this, you add up the number of 0 in each block. In other words, we force very much the number of 1 to be within the cell. But sometimes we have outlying process where the machine must provide service to a part that is not belonging to the subset. But you try to reduce this number. Okay, so here you see we have a ratio. That's why we thought of using the Dinkelbach procedure. Okay? Now, I won't go into all the detail because it would take too long, because I want to get rapidly to the model for this problem. But the objective function is try to maximize this quantity. So you can make a modification, and you you can specify very easily that this quantity is the same as 1 minus the sum of the 0 in the block plus the 1 out of the block divided by total number of 1 in the matrix plus the number of 0 in the block. So instead of maximizing, we specify a problem where we minimize. And in fact, we minimize this quantity. Minimizing this is equivalent to maximizing. So we minimize this quantity here. So to specify the problem or the model, we use two sets of variables. A set of variable xi, k, indicating if the machine I belongs to the block or the cell k, and yjk has a similar definition. It's equal to 1 if the part belongs to the cell. Okay? Good. So it's easy to specify the number of 1 out as this different where you use xik and yjk to specify the quantity. For instance, if we take, say, A1 out, this is the same as the number of 1 minus the number of 1 in the block. And the number of 1 in the block is the thing that's followed. You sum up over all the block, over all I and over all j. And whenever xi is in the same block as yj, then the product here is equal to 1, so you add up the 1 within the block. Okay? So this ratio here becomes the following in terms of the x and y variable. And you try to minimize this ratio. Okay? I will refer to nx and dxy for the numerator and the denominator, to shorten the notation. Okay? Good. So, the model, or the set formation problem model, is the following. You have the objective function here, as we specified before, and then the constraints are very straightforward. This is a very straightforward problem. Okay? You have to assign each machine to a cell. So you add up over all k, the xik, and must be equal to 1. You have to assign the machine to a cell. Similarly, you have to assign each part to a cell. And then we don't allow empty cell. That is to say, in each cell there is at least one part and one machine. Okay? This is to force the number of cells to include something. And the variables are equal to 0 or 1. So these constraints are specify an integer programming problem. In fact, it's binary. But the objective function is a ratio, and furthermore, it is quadratic. The numerator is quadratic and the denominator is quadratic. So the next step was to try to find an equivalent problem to where we eliminate the quadratic term. And we use a very standard way that we use to transform problem, binary problem, where you have quadratic term. This is a very straightforward way to do it. The idea is to replace each product here by a variable depending on I and j and k. And these variables are also 0, 1. So we maintain the binary characteristic of the model. Okay, now to specify the relation between the variable w and the xi and the yj, we add up the following constraints. Wij must be equal to 0 whenever one of the variables is equal to 0 here, right? And whenever both variables are equal to 1, then these constraints force the value of Wij to be equal to 1, okay? So, the model here becomes the following one. I indicate in red the modification or the connection between the variable w and the xi and the yj. Okay? So now I have a linear programming problem, and it is binary and it is fractional. So we use then the Dinkelbach procedure to deal with this problem. And we apply straightforwardly the Dinkelbach procedure to solve this problem. Okay? So let me summarize very rapidly the procedure, and we'll see about what kind of numerical result we can get. Okay, so to simplify notation, I will denote the feasible point to belong in the set x, y, and w. And so, in fact, the problem is to minimize over the feasible point the ratio of the numerator divided by the denominator. And the associated parametric problem